Good morning. Hope everybody's doing all right this morning. We are going to start section 1.1 today. And like I said, the slides are posted in the course content folder in Blackboard. So if you want to follow along that way, but those are the slides we're going to be using today. Just a couple of reminders about things that are coming up, though, before we get started. Just don't forget, yesterday you were supposed to send me the introductory email. So if you haven't done that already, please make sure I get that because that is actually a grade. So make sure you do that if you haven't done it already. The thing that's due tonight, there's two assignments. It's the orientation quiz and the academic integrity quiz. So just make sure by midnight tonight that you get both of those done. Again, those are the requirement for enrollment in the course. So just make sure that you get those done so that you don't get dropped. Okay, so I'd have to have them for sure by Monday at the very latest, but that's why I make it due so early. So just go ahead and get it done so that you don't have to worry about that. Okay, the next assignment that will be due is the getting started with WebAssign, which is actually in WebAssign. I saw a few people have already done that, so that's good. That also lets me know that people are able to get into WebAssign, which is good. If you're having issues logging in, though, please let me know as soon as possible so that we can get that resolved, okay? But make sure you get the getting started assignment done. And then the first actual homework assignment, homework number 1, which covers sections 1.1 to 1.4, is due Tuesday of next week by midnight. So as we go through these sections, I'm hoping to get at least into section 1.3 by today. So that should give you a good chunk of the information you'll need to complete a lot of that homework. So if you want to work on it over the weekend, you can. Okay. The only other thing is the Respondus Lockdown Browser tutorial that's due on Monday by midnight. So you've got all weekend to get that one done. But make sure that you get that done because, again, I want that done before the first test just to make sure that you don't have any issues with the Lockdown browser, that you know my expectations before you take the first test. Okay. Any questions, comments, concerns about anything before we get started today? All right, as always, if you think of anything, feel free to email me, or you can even type in the chat if you think of a question in the middle of class. I'll be happy to respond. So we will meet 4 times a week, yes. So that is to get our seat hours in, that's what we have to do. You are not necessarily required to be there. So the problem with, if you look on WebAdvisor, when you first look at a class, a lot of times it only shows like Monday, Wednesday, blah, blah, blah. But then when you actually click on it and expand it out, it'll show you there's like a Monday, Wednesday for 2 hours and a Tuesday, Thursday for 2 hours. And so that's where the confusion lies. Same thing in DataTel for us. So you have to make sure you're actually looking at the entire schedule. It does say that we meet 4 days, but I know it can be confusing and look like 2 days. If you can't be here for all the sessions, they are recorded. Remember, I'm not taking actual attendance during these sessions, so you can always go back and watch the videos if you need to. All I'm checking for in terms of attendance is that you're completing the homework assignments on time and the test on time. And as long as you're doing that, then you're not going to be dropped from the class, okay? You do not need to worry about signing that page. That's more for when I actually have a seated class. I'll pass that paper around and let people sign it, but I'm not going to require it. Just make sure if you have any questions about the syllabus, let me know so that I can address those questions. Okay. All right. Any other questions? All right, and like I said, if you think of anything else, just let me know. I'll be happy to answer any questions you got. All right, so section 1.1, 4 ways to represent a function. Now, in general, the first half of chapter 1 is a lot of review material from like pre-cal 171. So that's why we can get through these first 4 sections pretty quickly, I think. Once we get to the second half of chapter 1, then we get into some of the actual calculus stuff that you might not have seen yet. So we're going to go through and just talk about functions. What is a function? How do you represent a function? How can we represent word problems using functions? All that good stuff. And make sure that we really have that down, because that's going to be really important for us as we move into some of the calculus topics, to make sure that we understand what we can do and what we can't based off of what things are functions and what things are not functions. Okay. All right, so definition of a function. So it's going to be a rule that assigns to each element x in the domain exactly one element f of x or y in a set E. Okay, so we're calling D the domain. E in this case represents the range. X is our x values. F of x is our y values. So for every x, there's exactly one y value. If that's not the case, then it's no longer a function. Okay, so that's what we have to keep in mind. For every x, exactly one y. All right, so here we have the graph of a function, okay, because if we look here, for every x value in the domain of this function, there's exactly one y value associated with it. We want to find the values of f of 1 and f of 5. Okay, so looking at this graph here, if I want to find the value of f of 1, what does it look like that value would be? Three, good, right? So basically we just find 1 is our x value now, which is right here. We follow that up to our curve, which gives us a point right here, and we're trying to find the corresponding y value to that point, and in this case, that would be 3. So we can say that f of 1 is equal to 3. Any questions on how we got that? Okay. All right, now we want to find f of 5. Now this one you might have to just estimate. So what does it look like f of 5 would be equal to? Okay, so negative 0.5, right? So basically if we go over 1, 2, 3, 4, this would be 5 on the x-axis right here. We follow that down to our curve, which is right here. So it's definitely going to be negative, right, because it's below the x-axis. It's somewhere between 0 and negative 1. In this case, though, does it look like it's closer to the 0 or the negative 1? It looks like it's closer to negative 1, right? So rather than saying negative 0.5, which would be exactly halfway in between, what might be a better approximation for that value? Negative 0.75, negative 3/4, right? Same thing. Either one of those would be good, right? And even if you put like negative 0.7, negative 0.8, anywhere in the ballpark is fine for that approximation. Even in WebAssign, it leaves some leniency there for those points that aren't exact. So just know, as long as you're close in the ballpark, you'll be fine. Okay, but I would make it closer to negative 1 than 0. So negative 0.5 wouldn't be quite accurate enough in this case. Any questions on finding those values now? All right, now part B, we want to find domain and range. So let's start with domain. So we said the domain is just all the x values for our function. So what would be the possible x values for this function now? Okay, good, right? So we start at 0, right? Because this thing's not going all the way to negative infinity. It actually has a starting point right here. And we'll say that there's actually a closed circle at that point, since we're not given any open circles here. So we'll say that's included, and we'll use a bracket. And then if you count over here, that's going to give us 7 is this value right here. Again, we'll assume that that point is included. And so our domain is going to be from 0 to 7 this time. Whenever I'm asking for domain and range, I'm always going to ask for interval notation. So that's using the parentheses and brackets, right? Remember, brackets mean the values are included. Parentheses would mean that those values at the endpoints are not included. Any questions about how we got the domain here? All right, what about our range this time? So remember, that's our possible y values for this function. All right, so it looks like if we go down here, negative 2 is the lowest possible y value that we have on our graph, and it would be a point on the graph, so we're going to include it. So we'll start with negative 2. Highest point on our graph is right up here. That would be a y value of 4. Again, also included. So we can say that our range is from -2 to +4, both included. Okay. Any questions about how we got the range this time? All right, now, if I'm ever going too fast, please just either use the raise my hand feature or type in the chat and say, hey, hang on, I need to get something copied down. I'm always happy to go back and explain things. So just slow me down if I need to, okay? All right, example 2, we want to sketch a graph and then find the domain and range of each of these functions. So our first function that we're given is f of x equals 2x minus 1. So first off, what type of function is that going to be? What's it going to look like when we graph it? It's linear, good, right? So we're going to have the graph of a line when we sketch this graph. What do we know about this line? So what information can we get at 2x minus 1? Okay, good. So our y-intercept is going to cross the y-axis at -1. The y-intercept, that's our b value, is -1. What else do we know about this line? Okay, good. The rate of change is +2, right? Or we could call that the slope in terms of a line. So our slope, or the m value, is going to be 2. So now when we sketch this, we can start with our y-intercept. So here's our y-axis, here's our x-axis. So we're going to start at -1. I'm going to come down here. I'm going to put a point at -1 on the y-axis. So if our rate of change, or our slope, is 2, where am I going to go from there? Good. Up 2 and to the right 1, right? It's a +2, so we're going to go up 2 units, which will put us right here. Go over 1 unit to the right, which puts us right here. So we know there's going to be another point now at 1, 1. Once we have 2 points, we have all we need. If you want to do a third point just to make your line a little straighter, that's fine. But as long as your line goes through these 2 points right here, you're good. So this is what our linear function would look like, something like that. All right, now let's talk about domain and range. So what's the domain for that linear function going to look like? Good. -infinity to +infinity, right? So this is going to be all real numbers. There are no x values that we can't put into that function. And so when we write this now, remember, infinities and negative infinities always get parentheses. Okay, so just make sure you're putting parentheses on the endpoints there. So -infinity, +infinity, all real numbers. What about the range, y values? Same thing, good, right? So the range is also going to go from -infinity to +infinity. Again, we always use parentheses on infinities. Any questions about how we found domain and range for that graph now? All right, let's look at our g of x function now. So g of x equals x squared. What is that graph going to look like? Okay, it is quadratic, so it's going to be a U shape, right? So what do we call that? It's a quadratic U-shaped graph. What's the mathematical term we use for that graph? It's a parabola. Good, right? So we know this is going to be parabolic. So we're going to graph our parabola. Now let's think about what we know about the parabola this time. So what's one thing we know about it? Okay, good. Lowest point is going to be at the origin at 0, 0, and it's going to open up, right? So because it's a positive x squared, that's what tells us it opens up. Because we're not adding or subtracting anything, that's what tells us that the vertex, the lowest point, is going to be at the origin. So we start here at 0, 0, and I'm just going to do a rough sketch. You don't really need any specific points here. I'm going to open up like this. So that's what our parabola would look like this time. All right, now that we have that, let's talk about domain and range. What's our domain going to be for this function? Good, right? So just like the line, x values go from negative infinity to positive infinity, no restrictions on the x. What about the range this time? Perfect, right? So 0 is the lowest point in terms of y values. It is actually a point on the graph, so we're going to include it. So we have a bracket at 0. And because it opens up, it's going to go up to positive infinity. So that will be our range this time. Any questions about that graph or the domain and range for that one? So in terms of domain and range, I'm always going to want you to use interval notation. So if it's all real numbers, write it just like I have it here, negative infinity to positive infinity. Okay. Yeah, so those things mean the same thing, right? But in terms of all of my domains and ranges, I'm always going to use interval notation. Any other questions? Okay, so we're going to look at discontinuities when we get to section 1.8, and we'll talk about how we can actually write the domain in that case, right? You're going to have to break it up into multiple intervals using parentheses to indicate what values aren't included and that kind of thing. Okay, but that is coming. Any other questions? All right. So now we have a function 2x squared minus 5x plus 1. They tell us here that h can't be 0. That's mostly just because the expression over here has an h in the denominator. We want to evaluate f of a plus h minus f of a all over h. All right, so if we start with that expression over there, let's start with the f of a plus h piece. If I want to find f of a plus h, what are we going to have to do? Good, right? So everywhere that we see an x in our function, we're going to replace it with a plus h, right? So in this case, that's going to look like this. 2 times, and in place of that x, I'm putting a plus h, and that value gets squared. And we have minus 5 times, and instead of x, I'm putting a plus h. and then we have a plus 1. So that takes care of the f of a plus h piece. Now we're subtracting. I'm going to group all this together to make sure the whole thing gets subtracted. What are we going to do for f of a then? Good. Just everywhere you see an x, we're going to replace it with a instead. So this just becomes 2a squared minus 5a plus 1. So that's the f of a plus h minus the f of a. And then just remember we have to put all of that over h. All of this now is over h. Any questions about how I got that step? Okay, now at that point, now we need to simplify, right? So if we do this, what should we do first? Okay, so the stuff in parentheses. So when you say the stuff in parentheses, what would that be then? What would we need to do? All right, good. So go ahead and square the a plus h, right? Because if you look in all of your groupings here, there's no like terms, nothing we can actually simplify inside the parentheses. So we're going to go ahead and do our exponent here. I'm going to come out to the side. A plus h squared is the same thing as a plus h times a plus h. So what's that going to give us if we square a plus h then? Perfect. So a squared plus 2ah plus h squared, right? So we have to use FOIL there. A times a is a squared. The outer and inner terms both give us an ah, so that's where the 2ah comes from. And then the h times h for the last terms will give us h squared. So now I'm left with 2 times a squared plus 2ah plus h squared. Now we can go ahead and distribute here if we want to. So if we distribute the -5, that's going to give us a minus 5a and a minus 5h. Then we have our plus 1. And then same thing, because we're subtracting all of this stuff now, we have to distribute that negative. That's going to give us a minus 2a squared. This becomes a positive 5a and then a minus 1 at the end. Okay. Any questions on that step? Okay, what would we need to do next? Okay, so again, is there anything that we could do in the parentheses here? Okay, good. We can distribute the 2, right? So there's no like terms or anything inside the parentheses, so nothing to simplify there, but I can still distribute this 2 on the outside. So that's going to give us 2a squared plus 4ah plus 2h squared. And then I'm just going to bring everything else down for now. And then we'll talk about what to do next. All right, so now I've at least gotten rid of all of my grouping symbols, right? I've taken care of all the exponents I need to. Now it's just a matter of combining like terms. Okay, so if we start combining like terms here, what are we going to get? Perfect, right? So notice here the 2a squared, we have a positive 2a squared and a negative 2a squared. Those terms are actually going to cancel out. We also have a negative 5a and a positive 5a. So those terms are going to cancel out. And then we have our positive 1 and our negative 1. So those terms are going to cancel out. So the only things that are left here are the 4ah plus 2h squared and the minus 5h. That's all over h now. All right, now once you've combined all of your like terms, what could we do at this point to simplify this fraction now? Good. We have a common factor of h in the numerator, so I'm going to factor that out. So when we do that, that's going to leave us with 4a plus 2h minus 5. Again, all of this is still over h. Now, what could we do to simplify at that point? Good. Since we have a common factor of h in the numerator and denominator, those factors are going to cancel. And so really we're just going to be left with 4a plus 2h minus 5. No like terms, nothing else we can do to simplify that. So that's going to be our answer. Any questions about any of the steps for that one now? Okay, so this is what we call a difference quotient. Okay, this thing up here. This is going to be really important for us down the road because some of our definitions of things that we have to do are going to involve that difference quotient. So it's going to be really important that we know how to simplify it so that we can then actually work with this thing down here instead of that thing that we started with at the top. All right. Now, representations of functions. So there's basically 4 ways we can represent a function that we're going to look at. One of them is verbally, so just a description in words, so basically like a word problem. Numerically would be the next one, so that would be like a table of values where you have your x's and your y's just listed out. You could also have a visual representation, which would be like a graph, which we've looked at already. And then also algebraically, which are the formulas that we use, right? So actually recognizing linear functions, quadratic functions, things like that, based off the algebraic representation. Okay, so the goal here is going to be able to go between all of these different representations, right? Because we're going to want to take word problems and represent them algebraically. And then we might even want to look at a visual graph of those to be able to find key points and things like that. All right, so example 4, we do have a verbal representation here of a function. So it says when you turn on a hot water faucet, the temperature T of the water depends on how long the water has been running. We want to draw a rough graph to T, which is temperature, as a function of the time, little t, that has elapsed since the faucet was turned on. So we're not given a lot of information here, right? We just have to kind of think realistically, if you were to do this, what would you expect to happen, right? And then how would you actually represent that visually using a graph? So what's the first thing we're going to need to do if we're going to sketch this graph? Good, right? We need axes, right? Now, in terms of the axes, let's think first off, what kinds of values are we going to be worried about in this case? In terms of our little t, let's start with that. With little t, would we need positives and negatives, just positives? Where are we going to be? Just positives, right? Because we're talking about little t being time. We don't need to worry about negative amounts of time. Okay, so we're going to start with 0 as our time, and we're going to go positive from there. So when I draw, and this is going to be my horizontal axis, this is going to represent time. All right, now let's think about the vertical axis, which is going to be the big T, the temperature. What kinds of values would we need for that? So would we need any negative temperatures? Yeah, think about it, right? No matter what temperature scale you choose to use, right? And we're going to have to talk about that too. But whether it's degrees Celsius, degrees Fahrenheit, or even Kelvin, right? You're never going to have negative temperatures if your water's actually flowing, right? Because degrees Celsius, 0 would be freezing. Anything below that would mean you got frozen water. Your faucet's not going to run at all, right? And then Fahrenheit, you'd be at least 32 degrees before you're freezing. So you know you're in the positives, right? So there's no real reason to draw any negatives on this graph in terms of temperature. So I'm just going to draw my axis up this way. I'm going to label this big T. Now let's decide what type of temperature do we want to look at? So what units do we want to use here? Fahrenheit, okay? We'll call this in degrees Fahrenheit then. All right, now, once we've got everything labeled, now let's actually think about what this graph's going to look like. So as we start at time t equals 0, when we first turn on that faucet, what's gonna happen? Okay, it's going to start to increase in temperature right now. Is it going to start off way up here at the top, or is it going to be somewhere closer to the bottom? It's going to start cold, right? So it's going to be a lower value. Now remember, if we're doing degrees Fahrenheit, 32 degrees is freezing. So we know it's going to be above that. So it kind of depends on how you label these things. Most of your faucets are going to top out at maybe like 120 degrees, 130 degrees at the most. Okay, so I'm just going to say, let's just call this value up here 120 degrees, just so we kind of have a scale to work with. We know we're bigger than 30 degrees, but it's definitely not going to be hot yet. So I'm just going to start it somewhere in here. Okay, so around 60 degrees, somewhere in there probably. All right, now, like you said, it's going to increase from there. Now, as it increases in temperature, is that going to be like a line going straight up to as hot as it gets, or is it going to be more of a gradual curve? What do you think? It's going to be a gradual curve, right? Because usually, it's going to stay at that cold temperature for a little while, and eventually, right, the water will get through the pipes and it'll start to heat up. Okay, but it's not going to go straight to 120. So maybe it starts off cold and it gradually increases up to whatever that maximum temperature is, right? Now, once we hit that value of whatever the water is, right, the highest temperature it can reach, what's going to happen then? It's going to plateau, right? So we hit a point where it can't get any hotter, and it's just going to kind of level out. It's going to stay at that temperature, right? Because that's however hot the water actually is. Then what happens? Why is it going to decrease over time? Okay, so it depends, right? It depends on how much time has elapsed because in this case, right, it is going to stay hot, but eventually what's going to happen? If you've ever been in a house where you've got 3 or 4 people taking a shower at the same time, what happens? You run out of hot water, right? So if you have a tank on your hot water heater, eventually you run out of hot water in that tank. And what's going to happen then? It's going to start to decrease again, right? And it's going to get cold until it gets back to, whatever the ambient temperature, the temperature of the pipes in the room and everything, right? It's going to go back down to that temperature. So it's going to plateau at that temperature of whatever the water in the water heater is for a while. But eventually, if you keep running it, it is going to eventually decrease again, right? Because it's going to run out of hot water. Now, there are other variables, right? Because there are things called tankless water heaters that just constantly heat up the water as it flows through. And in that case, it would plateau and it would just stay there, right? And it would just keep running hot until you turn it off. But for most water heaters, right, that have a tank built in, once you run out of hot water, then it's going to start to get cold again because you don't have any hot water left. So without any numbers at all in this word problem, right, we can get a pretty accurate description of what this is going to look like just based off of real world experience, right? So that's what we're going to have to do in a lot of situations, right? We're going to have a lot of numbers in this class too. But I always want you to think realistically about the situations and the things that actually happen, okay? Because that's what's important when we're talking about these problems. Any questions on that one now? All right. Example 5. Okay, so now we've got another word problem. Okay, this time we are given some numbers though. So rectangular storage container with an open top has a volume of 10 cubic meters. The length of the base is twice its width. And material for the base costs $10 per square meter, while material for the sides costs $6 per square meter. We want to express the cost of materials as a function of the width of the base. Okay. What's the first thing we might want to do with a problem like this? Good. If you can sketch a picture, it's usually helpful, right? So what's our picture going to look like this time? Okay, so it is going to be some rectangular, but is it going to be two-dimensional? Okay, good, right? It's going to be a rectangular prism, right? So the base is going to be a rectangle, but it's going to be three-dimensional, so we have to make sure we're drawing it as a prism. So I'm going to sketch this. In 3 dimensions now. Okay. We don't know specifically, right? We know in this case that the base, the length is twice the width. So you can try to at least make that proportional, when you sketch your picture. But other than that, we don't really know anything about the height. Right, now, I'm going to go ahead and label everything that I know, right? Because in terms of a rectangular prism, we have three dimensions. We have width, we have length, and we have height. So in our picture here, I'm going to call this my width. This is going to be my length. And then the vertical is going to be the height. All right, now, based off the information that we're given here, what could we do now? All right, so let's make some formulas, right? So what formula are we going to want to use first? All right, so 10 times width times length. Okay, I like that because we know that it's $10 per square meter for the cost of the base. Now, remember though, we eventually want to get all of this in terms of width, right? So we're going to want everything in terms of W if possible. Let's see if we can do that first before we start applying all the dollar amounts. Okay, so let's see if there's a way that we can get everything just in terms of the width first. So what's something we know for sure? Okay, we know that length is twice the width, right? So we know that L is equal to 2W, which means in place of this length right here, I'm going to call this 2W instead. Okay. Is there a way that we could get the height now in terms of the width? Good. We know that the volume is 10 cubic meters, right? And to find the volume of a rectangular prism, it's going to be length times width times height. Well, if we set this up, then we know the volume is 10. We know the length is 2W. We know the width is just W. And then we have our height. Right, so now if I want to get the height in terms of the width, what would I need to do next? Okay. Let's see. So you did 10 over h equals 3. Okay, so let's be careful here with our multiplication, right? So if I multiply out the right-hand side here, what's 2w times w? 2w squared, right? So just make sure over here now we're going to get 2w squared times h. Okay? Yeah, so just be careful there, right? We're not adding, right? So we're multiplying, so just make sure you're adding the exponents. Now, once we do that, now we can get h by itself by doing what? Now we can divide, right? So I'm just going to divide by the 2w squared. So we'll have 10 over 2w squared equals h. And then we'll just simplify that, right? So 10 over 2 just becomes 5. This is just 5 over w squared equals h. So that tells me now that my height in terms of my width is going to be 5 over w squared. Any questions on that process to get everything in terms of the width? Okay. Now that we've done that, now let's look for our cost formula, right? So we're trying to figure out the cost of all the material to make this box. So, like we said, it's going to be $10 for the length times the width, right? Just the area of the base. So we know that I'm going to write this as C equals, we're going to have 10 times, and then if we do length times width, just in terms of W, that's going to be W times 2W. Now, we also need to consider the sides of this box, right? Now, it is an open top box, so we're not going to have a top, right? So we only need to worry about the base one time, but now we have the 4 sides going around. So how are we going to find the areas of those sides? Let's just start with this piece here. If I want to find the area of that front-facing side, how would you find that area? In terms of W, okay? So W times 5 over W squared, good, right? So it's the width down here at the bottom times the height of the box, which is 5 over W squared. So this is just going to be W times 5 over W squared. Now, what's the cost of material for that side? So this was $10 per square foot. Okay, 6 is the cost of everything on the sides here. So we just need to multiply that by 6 now. So we've got $10 times the area of our base. We've got $6 times the area of that side. Now, how many sides are going to have those same dimensions? 2 of them, right? So the front of the box and the back of the box will both be exactly the same. So I'm just going to multiply this by 2 now because I know that the cost of that material is the same and the area of the front and the back are going to be the same. Now I'm just going to put a plus here since we're going to add that cost to the cost of the base. Now, how many more sides do we have to work with? 2 more, right? So I'm just going to look at this one over here now. So I want to find the area of this side. And just like the front and the back, we know the left and the right are going to be the same also, right? So if I can find this one, then I can just double it and that'll give me what I need. How would you find the area of that side? Okay, so good, 2W times 5 over W squared. And again, what's the cost of that material going to be? Also 6, right? And we said already there's going to be 2 of those, so I'm going to multiply that by 2, and then we're going to add that. Okay, so that first line represents the cost of the base. The second one factors in the cost of the front and the back of our box. And then the third line here tells us the cost of the two sides, the left and the right. And again, there is no top, which is why we're not doubling the cost of the base, because it's going to be an open top. Any questions about how I got that function? Now, the only thing left to do is to simplify. Okay, so let's go through, see how we can simplify this. So that first part, 10 times W times 2W would give us what? Good, 20W squared plus. All right, if we simplify this next line now, what's 6 times W times 5 over W squared times 2 going to give us? Okay, so be careful there, right? It's not distributive property on that first line because there's no addition or subtraction, right? So it's strictly just multiplying all that together, which is why we get W times W is W squared and 10 times 2 is 20. Okay. So what would this next line give us now if we just multiply all of that stuff together? So what would just the numbers be? Let's start with that. 6 times 5 times 2. It is going to be 60 over W. Good. So 6 times 5 times 2 gives us 60. And then if we multiply W times, and then we have something over W squared, we're really just dividing W by W squared, which is going to give us a W in the denominator. We're left with 60 over W now. Right? And then the last line, it's going to be very similar. The only difference is we have an extra 2 here. So we're still going to have that W in the denominator. But because we're doubling this whole thing now, this is actually 120 up top now. Okay. And then our last step, we do have some like terms because 60 over W plus 120 over W, we have a common denominator. We can combine those. So I have 20 W squared plus, and then what's that going to give us if we add those two fractions together? Good, 180 in the numerator over our common denominator, which is W. So this right here would be the cost function in terms of the width for that box. Now, the reason it's so important to be able to get something like this all in terms of a single variable is because when we get to chapter 3, we're going to have word problems like this where we're trying to optimize the volume of a box or the cost of material for a box or something like that. And so being able to get it in terms of a single variable is going to allow us to do some of the processes we need to do to optimize those things. So any questions about how we did any of that here? right. Okay, so we want to find domain of each one of these functions now. And we're going to try to do this without graphing. So I just want to think about our rules for these types of functions where we might have restrictions on our domain. So the first one, we've got square root of x plus 2. So what do we know about square root functions in terms of their domains? Or another way to think about that is, what type of restrictions do we have? You can't square root a negative and get a real value, right? So we know in this case that everything that's inside there has to be positive or 0, right? Because we can't have any negatives inside. So how could we set up an inequality here to say that we can't have any negative values inside that square root? Okay. Good. So once we solve it, that's what it's going to be, right? So I'm going to start though with just the x plus 2, what's inside, has to be greater than or equal to 0. Because again, we can't have any negatives, but it could be equal to 0 and it could be positive, right? So we know the x plus 2 inside has to be greater than or equal to 0. Then once we solve that, we can just subtract the 2 on both sides. So now we have x is greater than or equal to -2. Any questions about how I did that? Okay, now that we have that, we want to write this in interval notation. What would the interval notation look like for x greater than or equal to -2? Good, so we're going to have a bracket on the -2, because we do want to include it this time. And then it's going to go to positive infinity since we want to be greater than or equal to -2. Any questions about finding the domain for that first function now? All right, let's look at the second function. Okay, so we've got 1 over x squared minus x. So what type of restriction are we going to have with this function? Good, right? So because we have a fraction and we have x's in the denominator, we know that denominator cannot be equal to 0, right? So anytime you've got a fraction, denominator can't be 0. So I'm going to start this by saying x squared minus x cannot be equal to 0. All right, now if I want to know the values of x that we can't use, what would I have to do next? Okay, so be careful here, right? If I add x to both sides, I'm going to do that out here to the side. I get x squared cannot be equal to x. And then what would you do at that point? Okay, so And the issue with that step, right, if you try to divide both sides by x, you might be dividing out possible solutions. Okay, so that's why you never want to divide by a variable that you're trying to solve for, is because you could be canceling out solutions to your inequality in this case that you don't want to cancel out. Okay, so that's why we can't solve it that way. What could we do instead, though? Factor. Good. So how would you factor x squared minus x? Good. So if we factor out the x, we're left with x minus 1. And now that I have my factors, now we can do what? Good. So set each factor not equal to 0. So x cannot be equal to 0. And x minus 1 cannot be equal to 0. Okay, so we know for sure we have a restriction at 0 then. And the other restriction then is going to be where? Positive 1. Good. So x cannot be equal to 1. Any questions about how I did that? Now let's talk about our domain in interval notation. So what's our domain going to look like this time? Okay, good. It's going to be all real numbers except for 0 and 1. So we're going to have to split this into multiple intervals to make sure that we hit all the values that it could be, but doesn't include the 0 and the 1. What would that first interval have to look like then? Good. We're going to go from negative infinity to 0. We don't want to include 0, so it is going to be a parenthesis. What would the next interval look like? Okay, 1 to infinity is another interval. I agree with that. I'm going to put it over here, though, leave some space because we're still missing an interval. Okay, so it's going to be negative infinity to 0, 1 to infinity. We also need to include all the decimal values between 0 and 1, right? So we need a third interval in here now that goes from 0 to 1. And then we are going to use a union symbol between each one of those intervals to make sure we're including all real numbers except for 0 and 1 this time. Any questions on that domain now? All right. Let's take a so use curly bracket and let's just cut noise. So I don't want, so the reason I'm going to ask for interval notation, one, it's cleaner, right? And two, in WebAssign, that's the only way it's going to let you enter your domains. And so that's what I want you to get familiar with. Technically, I mean, if you write it using set notation, I'm going to give you credit because it's not wrong, right? But I do prefer that you use the interval notation just because it's what WebAssign is going to use and it's what I'm really looking for on the test because it's just a lot easier. Okay. In general, right? I know sometimes it can get pretty long, but yeah, if you use the set notation, right, it's not incorrect technically, but I do prefer interval notation. Any other questions there? All right. Let's take a 5-minute break, okay, because I'm going for a while. So at 11:10, we'll get started back up, finish up this section, and get into the next section, okay? All right. Okay, so we're going to pick up then with example 7, or we'll talk about vertical line test first. Okay, so again, this is probably something you remember from pre-cal. Okay, but a curve in the xy plane is a graph of a function if and only if no vertical line intersects the curve more than once. This goes back to that definition of what a function actually is, right? That for every x, there's exactly one y, and that's why it has to be able to pass a vertical line test, because if a vertical line touches your curve at more than one point, that means that a single x value has multiple y values associated with it. Okay, so this is a way, if we're given the visual representation, the graph, then we can use a vertical line test to test if something's a function, rather than having to actually look at the way we did on the previous example to find those restrictions. Now, a function f is defined by, and does anybody know what we call this type of function? Okay, so we've got f of x equals 1 minus x if x is less than or equal to negative 1, and x squared if x is greater than negative 1. Anybody know what we call that?
Piecewise, I believe.
Okay, good. So this is a piecewise function. Label that here. Okay, so anytime you've got multiple pieces for different parts of your domain, that's what we're going to call it. Now, if we want to evaluate the function at f of negative 2, okay, which piece of our piecewise function now are we going to have to use, the top or the bottom?
The bottom.
Okay, so be careful here. If negative 2, right, think about in this case, is that going to be less than or equal to negative 1 or greater than negative 1? It is going to be the top, right?
Oh,
So
yeah, top.
negative 2 is less than or equal to negative 1. So we're going to substitute it into the top piece of our function here. So that's going to be 1 minus negative 2, which is going to give us what then? Three. Good. So 1 minus a negative 2 becomes 1 plus 2. And so we get positive 3 as the value of our function at negative 2. Okay, so that's the key with these piecewise, is just make sure that you're substituting into the right place. So just pay attention to that domain and make sure you know where it's located. All right, so now we're going to do f of negative 1. So same thing, I've got to figure out which piece of my piecewise we're going to use this time. So we're going to use the top or the bottom. Top again, good. So in this case, it's less than or equal to negative 1. Negative 1 is definitely equal to negative 1. So we're going to substitute into the top piece again. So we're going to have 1 minus negative 1. And that's going to give us what then? Positive 2. Good. All right. And if we look at the last one here, f of 0, which do we plug into this time? This time it's going to go into the bottom because 0 is greater than negative 1. So we're just going to square the 0, which is going to give us what? 0. Perfect. Any questions about finding those values now? All right, now the second piece of this is to sketch the graph. Okay, so we need to think about what this graph is going to look like. Let's start with the top piece of our piecewise function. What would 1 minus x look like in general? Just ignoring the fact that we have a restriction on the domain, what would 1 minus x look like? It's linear, right? And what do we know about that line? Okay, slope is going to be negative 1. Good. And what else do we know? Okay, the y-intercept would be at positive 1, right? Because you could rewrite this as negative x plus 1 if you wanted to. So we know the slope is negative 1, y-intercept is positive 1. So I'm going to think about this as starting up here at 1. And if it has a slope of negative 1, we're going to go where? Okay, you could go down 1 and right 1. Okay, so if you went down 1 and right 1, that would be here. But keep in mind here that we're only going to graph this line wherever x is less than or equal to -1. So what could I do instead to make sure that my line is only going to the left of -1 instead? Good. We could go up 1 and left 1 instead. So I'm going to go up 1 and left 1. And this is actually going to be the end point of that line then, because it would have started right here. Okay, but our slope is -1, so I can go up 1 and left 1. That's going to give me the point at -1, and that's where that line is actually going to end in this case. Now I want everything less than or equal to that, which means my line now is going to go up and to the left from that point. I'm going to do another up and to the left here, just to give myself another point on my graph. And so this is what this is going to look like. Any questions about how I got that part of the piecewise? All right, now let's look at the second piece, the x squared. What is that piece of the piecewise going to look like? It's a parabola. Good. What do we know about that parabola? Okay, it's positive, so it's going to open upward, right? And what else do we know? Vertex is at the origin. Good. So we have a vertex at 0, 0. We know it's going to open up, but we have to make sure that we're only graphing that parabola where x is greater than -1. What would the point be at -1 if it were included? It will be -1, +1, right? Because if I square a -1, it's going to give me a +1. So I know that I would have a point on my parabola at -1, 1. But because I'm strictly greater than -1, I'm going to have to put an open circle at that point. So right here, we're going to have an open circle. And then from there, I'm just going to sketch my parabola like I normally would. It's going to come down through the origin here, and then it's going to open up into the right. And that's what our parabola would look like this time. Any questions about how I got that piece of the piecewise function? All right. Absolute values. Okay, so in general, when you take the absolute value of a number, you are finding its distance from 0. Okay, so that means it's always going to be positive because we're talking about a distance. So in this case, we're going to define absolute value of a as long as a is greater than or equal to 0, and the absolute value of a is equal to the opposite of a, or -a, if a is less than 0. And a lot of people look at this and go, well, that's just counterintuitive. You just said that absolute values have to be positive, and now you're putting a negative in there. If we think about it, if a is less than 0, that means that a is a negative value to begin with. Well, if I take -a, then I'm basically taking like -2, right? Which means then that it's going to become what? Positive, right? So that's why we define it this way, is because if a is already a negative, we have to take its opposite, we have to make it negative, and a double negative now is going to become a positive. Any questions about absolute values there? All right, so now we want to sketch the graph of the absolute value function. Now, to do this, you might already know what the absolute value function looks like, and that's great. I want to actually rewrite this as a piecewise function. Okay, and the reason is, again, when we get into chapters 2 and 3 and we're working with some of these calculus processes, it's important to be able to think of this function that way. And so I want to think about how we could split this up now as two separate functions using a piecewise. And this is going to come back to that slide that we just looked at and what an absolute value actually is, how we define it. How do you think we could split this up into two separate functions then to get the absolute value of x? Let's start this way. Where do you think we would need to split it? So if we're splitting the absolute value function into two separate functions, what x value do we want to split it at? At 0, right? So that tells me then that one part of my domain is going to be everything where x is greater than or equal to 0, and the other piece then is going to be everywhere where x is less than 0. Now, if x is greater than or equal to 0 for my absolute value function, what would I want the function for that top piece to actually look like then? Okay, so we actually don't need to use x squared in this case because all that's inside the absolute value function is an x, right? So what would our function be equal to on the positive side then? So x is already greater than or equal to 0. It's just going to be equal to x, right? So we can just say the top piece of that piecewise is just x everywhere that x is greater than or equal to 0. What then would the other piece of our piecewise look like whenever x is less than 0? Negative x. Good. So just like we saw on the previous slide, right, it was equal to a whenever a was positive, and it was equal to the opposite of a whenever a was negative. Same thing here. We can split this into a piecewise function using x and negative x for positives and negatives now. Okay. Now let's think about what that graph's going to look like then if we were to sketch this piecewise. Again, you might already know what the absolute value function should look like, okay, but this should give us that same graph. If we were to graph x wherever x is greater than or equal to 0, what is that piece going to look like? Okay, so it's a line, right, just for the top piece, right? Eventually, yes, it is going to be a V, right? But just for the top piece, if we're graphing x, that's going to be a line that goes from 0 to positive infinity, has a slope of 1 and a y-intercept of 0. So we're going to go up 1 and right 1, and this would be the top piece of our piece function. What would the bottom piece of that piecewise function look like then? It's going to go from 0 to negative infinity, but it's going to be negative x instead, right? So it's going to be linear. And so in this case, the slope is negative 1, which means I can actually go up 1 and left 1. I'm going to have my linear function that looks like this on the other side. And then, Dean, like you said, it does become a V-shaped graph, right, which is what the absolute value function should look like. But those are the two pieces of the piecewise that would give us that V shape now. And again, the reason this is going to be important is at 0, 0, at the origin for the absolute value function, that sharp point prevents us from being able to do certain things in calculus. And so we need to be able to split it into these two separate linear functions so that we can operate on those individually. Okay. Any questions on that one now? All right. So now we're given the graph this time, and we want to try to write a formula for that function. And I'll tell you, there's more than one answer to this one, right? So looking at that graph, I will tell you it's going to have to be piecewise, right? So however you want to split it, it's fine. What would one piece of this piecewise function look like? Okay, so we could just use x, right? So if we start here at the origin, the first piece of this you could think of as a linear function that has a slope of 1, right? Up 1 and right 1. And so we can just say that's x. And what would the domain for that piece of our piecewise be? From 0 to 1, good. And so in this case, we would write that as 0 less than or equal to x less than or equal to 1. Okay, so we're actually writing out piecewise functions. We use the inequalities instead of just the interval notation. Okay, so that's what that piece would look like. Any questions about how we got that part? All right, so now we need to pick up at 1 and look at this next piece. What would that function look like then if we pick up at 1 now? Okay, so the slope is definitely -1, right? Because we're going down 1 and to the right 1. So I like the negative x. What would the y-intercept of that line actually be, though? Exactly, right? So if we were to extend this line out, recognize here that it would actually cross the y-axis up here at 2. And so we have to make sure that we're saying this is -x plus 2. Okay? All right, now, what would the domain for that piece be? And if you write the interval notation, that's fine. I'll convert it to the inequality. So what are the x values for that piece of our piecewise? Okay, so we've already gone from 0 to 1, right? So we definitely don't need to go all the way back to 0. So this part of the line only goes from 1 to 2, right? So we're only looking from this point to this point right here for that line. So it is going to be 1. We've already included 1 in the previous one, so I'm going to make this a less than instead of a less than or equal to. And then we could either make this a less than 2 or a less than or equal to 2. It's just that you can't include the same value in multiple pieces. So if I put less than or equal to here, then I have to make sure that my next piece does not include the 2. That's all. because that points in part of both, right? I can include it in either piece that I want to. All right, so now we have this last piece. So what is that function going to look like for the last piece of that piecewise? All right, so it is going to go from 2 to infinity, right? Which basically is just x is greater than 2. You don't actually have to put the infinity on that inequality. But what would that function look like? Zero, right? So in this case, we have a horizontal line, which is constant. It is on the x-axis, so that value is 0. And so we would just say that that's going to be 0 everywhere that x is greater than 2 or where 2 is less than x. However you want to write that's fine. So again, the key here, right, even though all these points are connected, you can't have a value included in 2 different pieces of your piecewise. So again, if you include it in one, you can't include it in the next one. That's the key there. Now, is there another way that we could have written this piecewise using 2 functions instead of 3? So look at this first part that goes, look at all the way from 0 to 2 together, right? So if I just look at everything in here now, what does that look like? Yeah, it's the absolute value function, but it's flipped upside down, right? And so if you remember back, we're going to do transformations in section 1.3 just to review those. Okay, but if you remember back to your transformations, if you put a negative out front, that's going to give you that reflection over the x-axis, which would flip it upside down. And so I could write this first part as an absolute value function that is negative, but it's also shifted, right? So it's not at the origin anymore. So now we have to think about the transformations if we were to shift it. I know it's shifted to the right 1 unit because it's not at the origin, it's at +1. How would I shift it to the right 1 unit? What would I have to put in that function now? A -1 on the inside. Good. I'm going to put an x -1 on the inside. And it's also shifted up 1 unit from the origin. And so what would I have to do to get that shift up 1 unit? A +1 on the outside. Good. And then in terms of the domain for that piece, now I'm going all the way from 0 to 2. So I'd say 0 less than or equal to x less than or equal to 2 instead. And then I would only need one other piece to this, which is the 0 from 2 to infinity. Okay. So just know in terms of your piecewise functions, occasionally, right, you'll be able to actually condense parts. And so in this case, because 2 of those lines actually meet at a point, you could write that as an absolute value function instead and get this down to 2 functions instead of 3. But again, we'll review those rules for transformations in section 1.3 also. All right, now, greatest integer function, we're not going to do a ton of work with this, but I just want you to be familiar with it if you see it. It's called the step function because it looks like a set of stairs, right? Basically, you're going to have a single value on some interval, right? So in this case, like from 0 to 1, it's all one value. Then when you go from 1 to 2, it steps up to another value. And then you go from 3 to 4, it steps up to another value, and so on. Okay, so you have all this series of horizontal line segments, but they're not connected. Okay, so that's what a step function is going to look like. Again, we're not going to do a ton of work with this, but if you ever see step function or greatest integer function, that's what it does look like. Right, now symmetry. So if a function f satisfies this criteria that f of negative x equals f of x for every number x in the domain, then we say that it's an even function. Even functions are always going to be symmetric with respect to the y-axis. Okay, so we can actually take the function itself, substitute a negative x in there. If we get the same function back that we started with, then we know it's even, and we know we have symmetry about the y-axis. If when we substitute a negative x in there, we get the opposite of the function that we started with, then we say that the function is odd instead, and odd functions are symmetric about the origin. Now, origin symmetry is actually rotational, meaning that you would take everything, like let's say you have values in the first quadrant, those would get rotated 180 degrees into the third quadrant. Okay, so just know that odd symmetry is actually rotational. It's not over a specific axis in this case. But in both cases, the test is going to be to plug in a negative x, see if you get the same function you started with, or see if you get the opposite of the function you started with. If neither one of those things happens, then it's not even or odd. Okay? All right, so let's see if we can test these to see if we have an even, odd, or neither function. So for part A, and our test is always going to be to find f of negative x. All right, so I'm going to substitute a negative x everywhere that I see an x here. So we're going to have negative x to the fifth plus negative x. Now we have to simplify. What is negative x raised to the fifth power going to give us? So if you raise a negative to an odd power, like 5, is it going to come out positive or negative? It's going to be negative, right? So this is going to be negative x to the fifth. And when you add a negative x, that's the same thing as subtracting x. Any questions about how I simplified that one? Okay, now the question is that the same function we started with? Is it the opposite of the function we started with? Or is it neither of those two things? So what do we think here? It's the opposite, right? So because it was polynomial to begin with and all of our signs changed, we can say this is the opposite, which means that it's what type of function then? It is an odd function. Good. Remember we said that means there will be symmetry about the origin if you were to actually sketch the graph of this one now. Any questions about how we got odd for that one? All right, so same thing on the next one. We're going to do g of negative x, which means we're going to substitute a negative x everywhere we have an x. So if we simplify this one now, what's that going to give us? Good, right? So the negative x raised to the fourth power just becomes x to the fourth because we're raising a negative to an even power this time. So we still have our 1 minus. That becomes x to the fourth. So now again, the question is this the same function, the opposite of the function, either of those things? It's the same. So if we get the same function we started with, what do we say? This one is even. Good. And again, graphically, that would mean that we would have symmetry about the y-axis this time. Any questions on that one? All right. So h of negative x, we're going to have 2 times negative x minus negative x squared. So again, simplify first. So if we simplify this time, what's that going to look like? Good. So we have a negative 2x, we have our minus, and then that becomes a positive x squared. So it's going to look like that. So again, is that the same, the opposite, or neither? This time it's neither, right? So even though the 2x became a negative 2x, the minus x squared stayed a minus x squared. All of your signs didn't change, so we have to say this is neither this time. All right, and so now we don't know anything about symmetry, right? There would be no symmetry either about the x-axis, or sorry, the y-axis or the origin. Okay, so that's what neither means. Any questions on any of those now? All right. So last piece of this section, okay, increasing, decreasing functions. So a function is increasing on some interval if f of x sub 1 is less than f of x sub 2 everywhere that x sub 1 is less than x sub 2 in that interval. That's a fancy way of saying if it's going up from left to right, it's increasing. And that's all you really need to worry about, okay? In this case, we're basically saying that this x value is less than this x value, and this y value is less than that y value. Therefore, it's increasing on the interval from x1 to x2, okay? On the other hand, if f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2, so now I'm going to look at this value and this value, b is less than c, but this y value is bigger than that y value, therefore it's decreasing on that interval now. But again, it's a fancy way of saying if it's going down from left to right, then we have a decreasing interval. Any questions about what it looks like for increasing or decreasing now? Again, you're always reading from left to right because your x1 is always less than your x2. So just make sure you're always reading from left to right for increasing, decreasing. All right. So section 1.2 is really a lot of definition, and so that's what we're going to look at next. There's not a ton of examples to do there. Let me switch over to that. All right, so mathematical models and a catalog of essential functions. So really, the focus of this section is going to be on the catalog part, just defining what the different types of functions are so that you recognize them, because again, it's going to be important to know what different types of functions you're working with, because different things can be done to different types of functions now. Okay? All right, so in general, a mathematical model is some description, usually with a function or equation, that models a real-world phenomenon. Okay, so we're going to be looking a lot of times at real-world situations, word problems, and trying to come up with a model that models that situation. Now, the most basic of these models is a linear function. Okay, so f of x equals mx plus b. Again, we've already looked at in the previous section. Okay, M represents your slope, B represents your y-intercept. But again, that's the most basic of our models that we can use. The next type would be polynomials. Okay, so a polynomial is always going to be in this form here. So we have a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on, all the way down to a sub 0, which will be our constant term. Again, don't get freaked out by the notation, because really all of these a values here are going to be numbers, right? So these are numerical values that represent the coefficients of that polynomial. X would be our variable here, and then all of the n's are your exponents, right? So we have n, then n minus 1 would be 1 less than that, all the way down until we don't have an exponent at all. Okay, so this would be like 5x to the 5th plus 3x to the 4th minus 2x to the 1st if you want it to be, and then plus 7, right? That would be a polynomial function. The key here is it's always going to be some number times your variable to some power, and you're always adding and subtracting those terms. Now, some terminology in case you've forgotten it from Math 171 pre-cal. The degree of a polynomial is whatever the highest exponent is on your variable. Okay, so in this case, that would be n, because that would be our highest exponent. The coefficients, again, are those a sub n's. All those values would be called coefficients. If you have a degree of 2, we call that quadratic. And again, we mentioned that in the previous section. And then we also can have a degree of 3, which we call cubic. 4th degree would be quartic. Usually you don't really go much above that. You would just call it a 5th degree polynomial or 6th degree polynomial and so on. They do technically have names. We just usually don't use them that often. Okay. So as long as you know quadratic for degree 2 and cubic for degree 3, those are the terms you'll see most often. Any questions about polynomials now? All right, power functions. Okay, so if you have a function that's just x to the a, where a is a constant value, we call it a power function. Now, it's possible that your a is just equal to n, where n is some positive integer, right? That would be the first type of power function. That's technically a polynomial. It happens to be a monomial, okay, but that's one type of power function. You could also have power functions, though, where the a value is 1 over n, which are actually become root functions, right? So remember, if you had something like x to the 1/3, that's the same thing as the cubed root of x. Okay, so x to the 1 still considered a power function. It's just that we have a fractional exponent now, which we could then also rewrite as a root. Okay, and then if we have negative exponents, still a power function. Okay, but those are what we call reciprocal functions, because if you had something like x to the -2, you could rewrite that as 1 over x squared. Again, still a power function, but now we call that a reciprocal function also, because it becomes a 1 over x to some power. Any questions about the different types of power functions there? And I know I'm going through this kind of fast. Remember, all these are in the slides, and the slides are posted in the course content folder, right? So you can always go back and review these if you need to. Okay, rational functions now is just a ratio of 2 polynomials. Okay, so the key here, the numerator has to be a polynomial and the denominator has to be a polynomial. That's the only way you're going to have a rational function. If you've got something other than a polynomial in either place, it's no longer a rational function. Okay. So remember, that means you can't have any square roots or anything in the numerator or denominator. Can't have any fractions within a fraction, obviously. It has to be polynomial over polynomial. And then algebraic now is kind of the catch-all for anything else that doesn't fit. So it's any function that can be constructed using addition, subtraction, multiplication, division, and roots, starting from polynomials, though. Okay, so just keep in mind here, if it looks almost like a rational function, but because you've got a square root in there, then it becomes an algebraic function instead. Okay, so that's why I said it's kind of a catch-all term to represent anything that can't really be represented by those other types of functions now, as long as it's just addition, subtraction, multiplication, division, and roots. Okay, and then our trig functions, this is where we'll stop for today. Just remember, sine function, we have the sine curve, it oscillates between -1 and +1. Same thing with cosine function. You're probably going to want to go back and at least review, what those graphs look like, because it will be helpful down the road with a lot of the things we're going to do. And so if it's been a little while since you've had trig, just taking some time to go back and remember those, as well as some of the relationships between the different functions, like tangent and sine over cosine and things like that. That will be very useful down the road. Okay. All right, so those are the different types of functions we're going to look at in this class. Again, that's where we're going to stop for today. So Monday, we will pick up at the beginning of section 1.3. This should give you pretty much everything you need to cover about half of the homework that's due on Tuesday at this point. Hopefully, we'll be able to finish up 1.3 and 1.4 because they're not terribly long on Monday. And then that'll give you everything you need for the Tuesday homework. Okay. Let me know if you've got questions. Send me those questions using the Ask My Teacher button in WebAssign if you have them over the weekend, and I'll be responding to those questions as I get them. Also, don't forget to look at the calendar just to make sure you're keeping up with all the due dates. Again, the things that are due by tonight, though, are the academic integrity quiz and the orientation quiz in Blackboard. So make sure you get those done. And by tomorrow, the WebAssign Getting Started assignment, make sure you turn that in. Okay? Let me know if you've got any questions. Have a great weekend, and I will see you all on Monday.